Hello everyone, welcome to my talk. I will be talking about some of the JVM internals, but the JVM internals and the JDK internals that I think are really important for every developer. Okay, so I'm not telling you that you will make use of everything that I will tell you through this presentation, but I think it's crucial to understand and remember about some things. Here you can find my Twitter handle, so feel free to tweet if you like this presentation or if there is something you dislike. So a few words about me. At the beginning, I'm on a daily basis working as a co-founder of DevSkiller. It's a platform which allows you to verify programming skills before inviting candidates for an interview, so it can save you a lot of time. And something that is different about DevSkiller when you compare us to our competition is that we we test real skills. So we test not only knowledge of the particular programming language, but also knowledge about of tools, libraries, and frameworks that you use on a daily basis in your company. Also, I work at Codarty. It's a small software house doing consulting services for bigger customers. I'm working as a trainer at Bottega, and I'm a program committee member of Devoxx PL. So if you think that presentations are poor, then you can blame me after my talk. At the beginning, I want to thanks to Martin Thompson and Alexis Shipilev, as many of the things I'm talking about are really complex. And big thanks to them for verifying the micro benchmarks and reviewing the slides. Okay, so now let's start. If you are a Java developer, then on a daily basis you work with Java virtual machine, okay? But when I ask people, what do you think that JVM actually is? So the answers are really complex, and there are really various answers, like some the runtime environment, etc. Yes, that's all true, but the simple answer is that it's just an application. It's just an application written in C++. Some parts in assembly, some parts in Java, but it's an application. What's common to all applications is that all applications have got source code. Okay, and JVM is also written by normal people. Okay, it's got source code which you can clone. You can open it in your NetBeans IDE because it's the only IDE that can open this source code and review, check what's happening. You can debug this code. You can build it and change, etc. Okay, so you can do such things so you can understand what's happening inside the Java virtual machine. And this virtual machine is really complex because often when we talk about the life cycle of our projects, it's really simple. We start with idea and we are finishing with the feature on production. That's great. That's something that is, let's say, the business understanding of the software life cycle. Okay, something that should be life cycle for us looks a little bit more complicated, which means we are starting with the source code. Okay, source code is the place where we code our ideas. Then we use the Java-C to convert the source code into the bytecode. Then the bytecode is loaded by class loaders, and then it's run in an interpreter. An interpreter is observing the code, is checking how this code performs, and then is optimizing the code using the JIT compiler. And then we finished with the optimized native code, which runs as well as code written in assembly language. Okay, and now I want to go through all those steps. So, how many of you have ever seen the Java source code? Please raise your hands. Okay, like 60% of the people, rest is slipping away. Okay, so this is the source code. This is the place when you put your ideas to compile it. Okay, and then we use Java-C to convert the source code into the bytecode. Okay, and there are a lot of, let's say, urban legend about what Java-C does or what Java-C doesn't. Okay, so Java-C mostly needs to do some checks. So it needs to check if the types are correct. Okay, it needs to check if the code should compile, if there are no some problems like you are trying to extend the final classes, or you are trying to override the final method, or you have created you have extended some class and you are not calling its constructor or something like that. Okay, so these are these checks. It also does some simple optimizations. Simple optimizations like when you use the string concatenation, it's converted to a string builder. Okay, so when you see someone using the string builder just to connect three separate strings, it makes no sense. Okay, it makes your code less readable, and it will still be optimized by JavaC. So at the very early stage. Okay, and that's pretty all that JavaC is doing, and it's producing the class file. Okay, when you take a look at your class file, there is a lot of information here. It starts with some magic number, which is a Cafe Babe. Okay, it's from the song of the Dreadful Dead or something like that, and it's used by Unix system to determine the file type. Okay, Windows systems are using the file extension, and Unix system are using the just the beginning of the file. So in Java, it's Cafe Babe. So every Java class starts with Cafe Babe signature. Then there are information about Java versions. So this code is compiled with the Java 8. It contains such fields. This is the access flag to the class, which class we are extending, etc. Okay, so there is everything. There's information about fields, about the interfaces, about the methods. There are method attributes, which also contains the method body, so the bytecode, etc. So everything is stored in a simple class file. Okay, and why it's important for us? Because as everything is placed in the bytecode, it means that after the compilation, I can change my bytecode. Okay, because bytecode, as the name suggests, it's just a list of bytes, where each byte means separate operation on the JVM. Okay, so how many possible operations can we put on one byte? 256. Yes, and that's a problem because for now we have more than 200 operations which are already used. So the problem is because Oracle is really limiting adding anything to the bytecode. And why it's important for us? Because when you compare the code you have written to the bytecode, it looks totally different. So do you know that in Java 7, Oracle has introduced the switch on strings? Yeah. Do you know how it works under the hood? So there is no support for switching on strings in JVM, which means JVM is getting the hash code of the string, is doing the switch on this hash code, and then it's checking using the equals method if this string is exactly this string, or it's just something which has the same hash code, okay? So it's doing some tricks just to avoid adding new bytecode operations, okay? But we can check those bytecode operations and see what's happening here. So I see that somewhere in my class code, when I take a look at the binary version of this file, there is 1b. 1b means that I need to load the first variable. iconst1 means I need to load the integer constant 1, okay? If compare not equal, then jump to the line 7, then load constant one more time, return something that I've checked here, so return 1, then load the object, load the variable, do some mathematical operation, etc., etc., etc. Okay, so everything is stored here, and if you use Java or if you use Scala or if you use Groovy, at the end you get the same bytecode. Okay, which means that at the end all is transformed to the same bytecode, which means that Scala, Java, and Groovy are doing the same. Are using the same JVM operations because there is no additional operations in JVM that are available only for Scala language. Okay, so that's how our bytecode and how our class looks like. Then we are using the class loader to load the class and turn it into the runtime runtime object, okay? There are different class loaders, and class loaders are dynamic, which means if you need some class, then class loader is going to load this class. But there is a hierarchy of the class loader. At the beginning, we have a bootstrap class loader, which loads just the JDK classes. So Java langstring, Java util list, etc. They are loaded by the bootstrap class loader, okay? And every class loader, before loading the class, checks if its parent contains this class. So if I need Java langstring, I ask the application class loader, he asks the extension class loader, ask the bootstrap class loader, ask bootstrap class loader is, yeah, I have this class, please. Here it is, okay? And why it's important? Because we have one bootstrap class loader, and we can have many extension class loaders, many application class loaders, and many custom class loaders. If you have a complex Java enterprise, so JEE environment, then you have a lot of different class loaders. For example, for every WAR file, you have different class loader, okay? And why it's important? Because sometimes you get an exception which tells you that user cannot be cast to user, which looks silly. You check the full qualified name. No. Com my company user cannot be cast to com my company user. It's something that is stupid, yeah? No, because there are different classes loaded by two different class loaders, and you are trying to put one object from one class loader to the other, and that's the problem. That's why we need to care about that. And for example, in JBoss or in other advanced systems, you can customize this class loader layout which you want to use and why you want to use it, okay? And the class loader, loading the classes is not cheap. It's really complex process. And why should we care about this project? Because at the beginning, we need to load this file, so we need to read the class definition from the file, and that's pretty easy. But then there is a verifying stage. Why verifying? I've used the Java-C to produce the code, yes? Yes, but I can also use some libraries to convert this code, okay? There are a lot of libraries that are modifying the bytecode by waiving some aspects or doing any other stuff. So then this JVM must validate this input. And why it's important? Because a few years ago, I think like 2 years ago, when Java 8 was introduced, they fixed the bug. Everyone knows that if you are constructing a class, and you have some class that you're extending, the first instruction, the first line in your constructor must be to call to the super class, okay? And that's something that is specified in the JVM specification, but JVM was never checking if it's true, okay? And then they say, so we need to check it. So they've fixed the code, added this check, and then the whole Java world has exploded. Why? Because CGLib wasn't calling the superclass constructor as the first line. It was like the fourth line, fifth line, and that was the problem. So every application was unable to start due to this bug. Okay? So they needed to break it one more time to make the Java developers happy. So that's the problem. But this is due to the verifying stage. Then we need to prepare the space for the class, so allocate the memory, and we need to resolve all dependencies. So if you have your class, which is called the product, and product has a link to the user, has the field of the user type, we need to load the user using the resolving phase, and then we also need to initialize the class. And now the class is ready to be used, so we are starting to execute this class in the interpreter, okay? Interpreter is Java, is really smart because it's called the template interpreter, which means it's not fully interpreting the code, it just has generating the templates. When you start the JVM, it's generating the templates for every single bytecode operation. So when you see that it's iconst1, it generates the bytecode operations that are optimized for your particular environment, for your operating systems, for your kernel, for your CPU architecture, etc., that will load the constant one, okay? And then it just takes the particular set of assembly operations from the array containing those informations, okay? And then hotspot, or the JVM, starts to monitor this code, check the performance of this code to detect the hotspots. The hotspots are the functions in the program that are called the most frequently. Okay? And the name hotspot, which is the name of the Sun or Oracle JVM, comes from this one single feature. Okay? And what does the JVM, what the JVM is doing after seeing that, okay, this method is really hot. It has been called like 2,000 times in the last second. Okay? It uses JIT to optimize this method. Okay? What is a JIT? It's just-in-time compiler. So it compiles the method when it is needed, not ahead of time, okay? Only when this is needed. So it optimizes the code and it compiles the methods into the native code. So the result of the JIT work is like you will be coding in C++, and even better, I will tell you why better, okay? And if you remember the minus client or minus server parameters, which were used a few months ago, really widely in the Java environment, the main reason for those parameters was to choose one of two different JIT compilers. So C1, which was the client compiler, it was cheap and not so efficient as the server compiler, which was very efficient, but it was also resource consuming to produce the optimized code. Okay? And is it worth to care about the JIT? Yes, because code which is optimized by the JIT can run up to 20 times faster than interpreter code. Okay? 20 times, it's generally a lot. Okay? But what JIT is doing that this code runs up to 20 times faster? So there are like 200 different optimizations that JIT can apply to your code. But I will just go to few really significant to show you how it works. So the most important optimization that is available in the JIT, we are telling that it's the mother of all other optimizations, is the inlining. So what does it mean that it's inlining? So when you see such code like here, we are usually doing the extract method to make this code more looking more Uncle Bob, okay? And JIT is doing something in the opposite. So when it sees something like this, supplier.get, and there is a business method which have something that gets string from supplier, which is a call of this method, then JIT is saying, okay, so I need to inline this code because invoking this method when this method is so small makes no sense, okay? So he's just inlining the call. And why it's important? Because now JIT or the Java can see much more than before. For example, imagine that in this get string from supplier at the beginning there is a null check. So we are checking if the supplier is not null. It makes sense, yes? But after inlining, when I will put this null check here, now it doesn't make sense, okay? I see that string supplier is not null because it's being constructed one line above, okay? So I can throw away this whole code because it's not important right now, okay? So JIT can apply a lot of different optimizations thanks to the inlining, okay? And for example, there is some optimization called loop unrolling, okay? I saw some developers doing such optimizations, but it's generally not the best idea. So when JIT sees that there is such code that like there is a for loop and we are iterating through the options and we are calling the process, okay? There is some additional cost hidden by the loop because we need to check if there is next element or something like that, okay? Which makes no sense. So JIT is unrolling this to those 4 elements. If you are, for example, iterating over the array, which has like 10,000 elements, JIT will probably unroll it, and it won't be a for I equal to 0, I plus plus, but it will be I plus 10, and inside the loop, there will be process I plus 1, I plus 2, I plus 3, I plus 4, etc. Okay? So it will unroll just to do all these backward checks not so frequent. Okay, so that's the next optimization. Next optimization is the scalar replacement. So take a look at this code. I have something like this. I'm constructing new point because then I need to call the store point method, which takes the point as its parameter. Okay? Can I optimize anything here? No. But let's try to inline this code. After inlining, I see that the store point calls the method event store added point point.x point.y. So now I don't need to instantiate this point. I can just explode its fields, okay, and allocate them on stack instead of the heap. And that's what we call by the scalar replacement, because after a scalar replacement, this code looks like this one. So there is no object allocation because it's not needed. We only need the fields of this object, not the whole structure, okay? So as long as you are not doing anything special in the constructor, JIT can optimize it and you won't be allocating this object, okay? Then we get something which is a pain in the neck for doing micro benchmarks, which is called the dead code elimination. You are trying to benchmark some code. It's really complex code, and you see that it was executed in 2 milliseconds. So you make this code 10 times more complicated, and it also takes 2 milliseconds. Why? Because JIT has turned something like this into something like this, which you can change the threshold, but the result will be the same. There will be nothing, okay? So that's the dead code elimination. But also we can do much more complicated things like lock elision, okay? So you are synchronizing on this result. But let's say that JIT, after doing its operation, sees that this result list is not escaping, okay? So it makes no sense to lock on this element because locking produce you additional costs, okay? So it's not locking, so it's just removing this synchronized element. There is also something called the type sharpening. So we have a list of users, but now we see, okay, it's not a list, it's always a narrow list. So I don't need to do the interface calls. I see, okay, this is always this class, so I can do some more advanced optimizations because I know that this is always an array list. So for example, I don't need to apply the instance of operator because I know that it's array list, okay? Because I've sharpened the type. And last but not least, it's my favorite, it's called OnStock Replacement. So when you start iterating over the giant loop, okay? And JIT finds out that, okay, so this loop is already like 15,000 iterations, and there will be probably much more. So please keep going, but I will compile this code, and at some point of time, I will stop the iteration. I will take this code, which is interpreted. I will throw it away, replace with the compiled version, and restart from this point when we have finished, okay? So the JVM can replace the method on the stack trace, okay? So it takes the interpreted stack, throw it away, replace with the native. Now go on. It's 20 times faster, so it's worth to do that, okay? So it can convert the interpreted stack into the native stack, okay? And I told you that the minus client and minus server is no longer used. Why? Because they've introduced something called the tiered compilation. What is the tiered compilation? Okay, it means that our code is not just 0 or 1, interpreted or compiled. There are many different stages for the code. So the code can be interpreted. It can be compiled with the simple C1 compiler, limited C1 compiler, full C1 compiler, or C2, so server compiler, okay? And usually it looks like we are starting from the interpreted code. When JIT finds out that this method is hot, it's being compiled to the third level, so full C1 compiler. Then when this method is being used and used and used, then you say, okay, so I need to optimize it even more. So it compiles it into C2 level. Okay, and now this code is fully compiled, but it still can be de-optimized to level 0 when the JIT finds out, okay, so this is not longer only an array list because you have changed something. I'm using some other branch, you have loaded some classes, so the context has changed, and now I need to de-optimize it and start one more time. Or the result I expected is not so good, so I need to de-optimize, try it one more time because it was uncommon trap, okay? Okay, great, but why should you care about such things? Because of two important reasons. First is that JIT is doing a lot of optimizations that you could do in your code, but JIT is not obfuscating your source code as your IDE, okay? I can inline a lot of code. I can do a lot of premature optimization, and it makes no sense because JIT will do the same in half of a second, okay? So please, remember that your code needs to be readable, and JIT will do the rest, okay? But also, something that is important, that if you are doing the performance or load test, they need to be run on the application which is already hot, which is already optimized. Okay. Why? Because optimized application runs 20 times faster, up 20 times faster than not optimized application, okay? So how can we track if our application is already hot or not? So we can use Jstat. It's a tool that all of you have already installed on your computers. So we can just launch it with the minus compiler, add the PID of your application, and time window like 1 second. So every second it will show you how many compilation has occurred in the last second, okay? When you see that there are 20,000 compilations every second, it means that your application is still being optimized, okay? After some time you will see, okay, there are no more optimizations done by JIT, there are no more compilations done by JIT, so now I can start measuring my application, okay? And then your results will be stable, and then you can say, okay, now it makes sense. Now my results are good, okay? We can also, of course, use it, and if you are going to do some performance tuning, you can measure your application before doing this tuning until it's not hot, okay? So just after starting, then do some performance tuning and check the hot application, and you will get 20 times faster, 20 times bigger throughput, okay? Okay, so now let's move to the other stage, which is the execution components. So we, at the very beginning, we have a program counter, which has an information about the current instruction, the frame, and the stack, okay? I think that every one of you have seen the stacktrace, okay? It's a daily basis of Java developer. But I should know that this stacktrace is built from frames, where every frame is just put on top of the stacktrace. Why is it important? Because are you familiar with this view? Yeah. Yeah, so something that was happening to me all the time is that I've put F7 or F8 too many times. I need to start one more time. No, you don't need to start one more time. You can just drop the top frame and start from this moment, okay? Because there are frames. You can drop it, okay? You can force the return value. This is just frames, okay? So you can play with it, and it will be much more efficient, okay? So now let's move to the memory layout. Memory layout in JVM is really complicated, okay? It's divided into two main areas, where first is the heap and the second is off heap, okay? So the heap is divided into young and old generation, and heap is the space where our object are living. Okay, when you create an object, it's allocated in the young generation, then we are running the garbage collector, the next garbage collection, the next garbage collection, and when JVM says, okay, this object is really old, let's put it into the old generation, so into the tenured space, okay? Then we have the off-heap area, which is a native area since Java 8. It has a meta space, which contains all the JVM data like constant pulse, bytecode of the methods, field and method metadata, all reflection data, etc. So these are elements that are needed by the JVM to run. Okay. Then you have a code cache, which is a place where JIT can store its result, and then you have a space for the threads, so the stacks, the program counter, and a lot of native areas. Okay. And why it's important to know about this memory layout? Because as you can see, the XMX is just here. Okay? So many people think that when they set XMX to 4 gigabytes, it means that their Java application will be using 4 gigabytes of memory. And that's generally not true. It can use even 16 megabytes of the memory, even if for heap we use only 4 gigs. Okay? So when you have like 10 gigabytes of the memory, it doesn't mean that you can run 2 applications, each using 4 gigabytes of heap. Because the meta space, code cache, and the threads are using, let's say, 2 gigabytes of the memory, 1 gigabyte of the memory. Okay, it's a lot, especially when you think about the microservices, and you're launching a lot of microservices, and your application is swapping. When application is swapping, you can forget about the performance because there will be no performance at all. Okay, let's move on now to the object layout. So we saw the layout of the whole application, and now let's take a look at the layout of the particular object. So for every object, we need to allocate the header, which contains a lot of information like the hash code of the object, which class does it represent, etc., etc. And there we have something like the integer, which is a product ID, and the string, which is a product name. And this object takes 24 bytes. Why 24 bytes? Because every object in Java must be, let's say, the multiply of the 8 bytes. Just due to alignment, so the JVM is able to calculate the addresses of the objects much faster. Okay? So, as you can see, the problem is that between using small integer and the integer wrapper, there is a big difference of size, because just an integer takes 4 bytes and there is no object, and the bigger integer, big integer, takes 16 bytes, so 4 times more. Okay? When you consider a boolean, the small boolean takes 1 byte. Okay? And the big boolean takes 16 bytes. Okay? So 16 times more. And let's see what will happen if we will add another integer. Our object is still only 24 bytes. Okay? So now let's add one more small, tiny boolean. It's 32 bytes. Why? Because there is alignment between the primitives and the objects, and then alignment for the object. So it's 32 bytes. Okay? And if we say, okay, so our application is eating too much memory, let's extend the heap to 34 gigabytes. Then our object will consume 40 bytes. Why? Because now we cannot compress the pointers to the object, so now it takes 8 bytes, and the header is 16 bytes. Okay? So you need to think about your object. It doesn't mean that you need to check the layout of all objects in your application. But if you have some really big arrays or some objects that are really fragmented in your application, means there are millions of those objects, it's good to check the object layout, because maybe by changing some integer to the int, you can save a lot of space. And when you have less objects, it means that garbage collector has much less work to do. Okay? And the garbage collector is something that is really important for the performance of our application. Okay? So garbage collector needs to cleanse the memory, and it's using complex vector algorithms, which often needs to stop your application, stop all application threads to do its job. Okay? So it takes a lot of time and for applications using like 8 gigabytes of memory, it can be even 40 seconds. 40 seconds is usually longer than the HTTP timeout, which means your users are doing requests to your application, and your application is doing timeout, garbage collector, okay? Which is a huge problem. And there are a lot of different GC algorithms that you can use, and some of them are for the high throughput, some of them are for the high latency, okay? There are a lot of informations about the garbage collectors. Something that's important for you is just to choose the right garbage collection algorithm, which will do the job, okay? If you're using the web application, probably the G1 is the best shot at the beginning, okay? If you're using some backend batch processing, then parallel is the fastest possible algorithm that is provided in the JVM, okay? So now let's move to the other part, which are the generics. Every time when we talk about the generics, we talk about the type erasure, okay? So we know that there is no generic information at runtime, only in the compile time, which is a bullshit generally, because there is a lot of generic information in the reflection, okay? There is generic information on all declarations. So when you have a class pilots where it implements the list of pilots, this pilot information is available in runtime. When you're extending the class, it's also available in runtime. When you have a field, which is a list of pilot, there is also generic information in runtime. Return type of the method, also generic information available in runtime. Method parameter, also generic information in runtime. So what does it mean that we are erasing the type? So when you access the object, not the field metadata, but the object, there is no generic information. But when you add two brackets, there is generic information. Why? Because this means we are creating the anonymous class, which is like here, so there is the generic information, okay? So it doesn't mean that this generic information is not available. You can access generic information like here. Pilot class, get generic superclass, you get something like this. My class, get declared field, get generic type, no problem. Field, get class, get generic superclass, oh, there is no information. I'm not accessing the field object, I'm accessing the object that's referenced by this field, and there is no generic information. Add brackets, no problem, generic informations as well as here. Okay? So, this is about the type erasure in generics. So, there are different dispatch types in Java. Okay, which means we can invoke just a normal method, we can invoke the static method, we can invoke the special method like constructor, and we can invoke dynamic method. Invoke dynamic is something that allows us to use lambdas, because lambdas in Java are generated by Java-C. They are not available through the construction. Like you can use this arrow, but it's generated, it's the method generated by the Java-C. It's bootstrapped using the lambda metafactory class, and it's called with invoke dynamic. And how it looks under the hood. When you take a look at the code generated by the Java-C, when you have something like this, so it's account get credit entries, and we have a static method generated which is called lambda $sum credit entries $0, which means it's a lambda inside the method called sum credit entries, and it's the first lambda. And it takes just one parameter, account, because it's lambda, it's the function operating on accounts, okay? Then we have a second option, which is exactly the same, but this method is no longer static. Why? Because I'm using the instance parameter inside this lambda, which means that this lambda is not stateless, it's now the stateful class. And what will happen if I will use some object or some reference that is just a parameter of this method? Okay, then I need to use it, I need to pass it to my lambda, so this lambda one more time can be static, and there is additional parameter which is this period, okay? Why it's important? Because you won't see it in your source code, but you will see it on your stack traces. So then you need to know what's happening and what does it mean, okay? So What about the method references? It's the same as lambda, but we don't need to generate the method because we are calling the method, okay? And let's take a look at the performance of this one, okay? So I've checked the performance or normal virtual calls, lambdas, and method references, and they're exactly the same, okay? So there are no performance reasons or performance-related reasons to use lambda or method reference or baseline, okay? Just remember that this code should be readable because the performance is exactly the same. Okay? So now let's move to the streams. The streams is something that is the really big thing in Java 8. It allows us to do a lot of quite nice features. Like there is an API for collection processing. So I can split my implementation and business logic as well as, for example, using declarative transaction management, okay? So there is no for, if, but there is a simple, let's say, DSL that allows me to process the collection, okay? And it doesn't store the elements, so it's just a pipeline that produces your final results. And why it's important that it doesn't store elements? Because it means that it's lazy. And laziness gives us space to optimization. Why? Because if you need to filter out the whole collection, then convert it to do something else, and then you need to get just the first element, it makes no sense to process the whole collection. Because when I get the first element, I can finish my work, okay? So let's take a look at the performance of the streams, because there are many urban legends about the stream's performance. So I've checked the performance using such simple string, which is mapping the collection of the integer of the strings to the lowercase, then filtering it, choosing just the strings which the fifth character is higher than 5, and then I'm mapping it to the substring from 6 to 12. Okay, and then I'm collecting it to the list, and each string is around 24 chars. And when we take a look at the benchmarks, when I use half of a gigabyte of the memory, then we can see that for 100,000 elements in this strings array, I get like 6,000 microseconds for the for, almost the same, like 10% more for the stream, and a half of this for the parallel stream, which looks good. But let's see what happened when I take the 1 million of elements, okay? For 1 million elements, I get 100,000 for the for, the same value for the stream, and like 40% more for the parallel stream, which looks strange because parallel stream, they were saying that they are so fast, okay? But let's see what's happened for 2 million elements, okay? 700,000 for the for, 700,000 for the parallel stream, GC overhead limit exceeded for the parallel stream. Okay, that is strange. So let's check what's happening when I compare the allocation rate. Okay, so for the for and stream, I'm allocating like 7,000 kilobytes per operation. And for the parallel stream, I'm allocating like 30% more objects just for the same run, which is causing the GC limit overhead for the bigger collections, okay? Because the parallel streams are using much more memory here. And if I just ignore the memory, then it's one more time, like 4 times faster, which is cool. So let's sum up this one, okay? Streams are definitely cleaner and more readable than looping, okay? Serial streams have similar performance and overhead to manual looping. Parallel streams are really fast, but they bring much bigger memory overhead due to storing the partial results, okay? Because parallel streams need to divide this work into many different threads and then combine this work, okay? And storing the partial results for every thread costs memory. And this cost is really high. Also, the problem with parallel streams is that they're always using the same thread pool. Okay? By design, they're using the common pool, which is available for the fork-join pool, and it's not designed to allow you to use your own pool. Okay? We can hack it for now, but this hack will be probably removed in the Java 9. Okay? So by design, you need to run all parallel threads on the same thread pool, which consists like 8 different threads, which is a big drawback of those streams. Okay? And the last thing I want to mention, these are the exceptions. This is a standard exception. Client already exists exception. Okay? And let's see what's the cost of throwing exception in Java. It's not so significant because it's like 1,000 nanoseconds. Okay? So it's not much. But the question is, do I need the full stack trace in all exceptions? Okay? Because I can use something that is called the stackless exception in Java, which means I'm throwing the exception, but I don't care about the stack trace. Why? Because I know the client already exists exception can be thrown in only one place of my code, and it's a business exception. So I can override the fill in stack trace method just to do nothing. And then situation is different, because now it's not 1,000 nanoseconds, it's just 18 nanoseconds. Okay? Is it important optimization? No, at all. 1,000 nanoseconds is nothing, usually. Okay? But the question is, if you want to get the whole stack traces in your logs when you don't need it. Okay? So then, if you don't need the whole stack trace, then the overhead for logging those lines, sending them over the net to your Kibana or Logstash or something like this, it's much more bigger than just throwing an exception. Okay? So that's generally all I want to say. If you are interested in the JVM, if you want to know more about what's happening here, there is a great book by Benjamin Evans and James Gott. It's called Optimizing Java. It's not yet written, but there is already like 30% of this book, and this is a really great book. Those 30% are brilliant, okay? Yeah. So there is also the Well-Grounded Java Developer book by the same author and Mighty Verwoerd. It's also a great book, which is doing as it suggests. It's grounding the Java developer knowledge. There are also 2 performance-related books. They're talking more about just the performance and how to tune applications than just about Java. And this is Java Performance by Charlie Hunt and Java Performance, the Definitive Guide by Scott Oakes. I saw that this one is available in the already store, so you can buy it here. It's like 40% discount, I think. And if you want to know more, there are tools that are available, okay? There are a lot of tools in JDK, like JMap, Jstat, JCMD, etc., that you can use to dig into your JVM. You can use Visual VM or Mission Control, Java Mission Control, to check what your application is doing, okay? To verify how your application is performing, etc. You can also use profilers like JProfiler or Honest Profiler to check what is the cost of calling this method? What is the cost of doing here? Okay, I see that this method is executing 10 seconds, but what does it do? What are the parts of these elements? And there is also a tool called Java Object Layout, which allow you to just check the layout of your object really simply by using ID. Okay? And if you want much more, then it's good to read the Java Virtual Machine specification or clone the source code and use the JMH tool. JMH is the tool I used to do the micro benchmarks, so we will get a lot of different answers. If you are just asking if it's better to use this hashing algorithm or this hashing algorithm, you just don't need to guess, okay? You can measure it and check, okay, so this hashing algorithm is faster, it's using less memory, so it's better, okay? So don't guess, just check. And if you want to see the codes of my benchmarks, they're available on my GitHub account, So JVM dive benchmarks, and you can find all benchmarks here. And I think that we don't have time for questions, but I will be here, so if you want to ask me about something, then feel free. Okay, thank you very much, and welcome to break.